Right now, a piece of technology lighter than a toaster is hovering in midair, resisting 40-mile-an-hour wind gusts, reading millions of data points every single second, and recording hyper-crisp video. Think about this. If a single microchip in this machine fails by a fraction of a millisecond, the entire unit plummets out of the sky like a stone. Most people see a sleek gadget fly over a park, but they never ask how a collection of raw dirt, oil, and rock turns into an anti-gravity flying supercomputer. Today, we are going inside the ultra-classified, hyper-automated factories where these skybound leviathans are born. Imagine taking 1,000 separate components originating from 5 different continents and forcing them to fit together within a clearance margin tighter than a single strand of human hair. You are looking at a process that fuses deep earth mining with high-speed aerospace physics and artificial intelligence vision. But here's what nobody tells you. Building a drone isn't just about assembling parts. It's about conquering the constant, ruthless pull of gravity. Step behind the airlock double doors of the world's most advanced manufacturing facility, where robotic arms move faster than a human eye can track, and dust particles are systematically hunted down and destroyed. We are about to track every single gram of raw earth from deep underground, through searing hot chemical furnaces, all the way to the final, terrifying stress testing chambers. And this is where it gets truly extraordinary. Because before this drone can even touch the sky, it must first survive an environment hotter than a desert and colder than the Arctic. Long before a drone ever takes flight, its story begins deep inside the Earth, under conditions of crushing pressure and subterranean heat. In the scorching open pit mines of Inner Mongolia and Australia, heavy diesel machinery carves out thousands of tons of raw, or to extract rare earth elements like neodymium, dysprosium, and terbium. These exact metals are refined to an unbelievable purity of 99.99%, traveling over 6,000 ocean miles inside heavy steel containers to reach the motor production line. Without these specific elements, the high-torque, ultra-lightweight brushless motors that keep a drone airborne simply could not exist. Now, look at the drone's ultra-rigid skeleton, the carbon fiber frame that gives it strength without adding weight. The journey starts far away on chemical refining farms and petrochemical plants in Japan and South Korea, where precursor polyacrylonitrile fibers are drawn into strands 5 times thinner than human hair. These synthetic fibers are spun into heavy spools weighing up to 500 kilograms, costing over $50 per kilogram, before being shipped under strict climate control. Most people never think about this, but the moisture levels inside these shipping containers fluctuate by even 2%. An entire multi-million-dollar batch of carbon fiber precursor material is completely ruined. Then come the nerve centers, the silicon microprocessors, optical glass, and high-purity copper windings. Pure quartz sand from quarries in North Carolina is melted down inside electric arc furnaces at a blinding 1,600 degrees Celsius to form hyperpure silicon ingots. Simultaneously, ultra-pure copper wire, refined to 99.995% purity, is pulled through diamond dies across thousands of meters of machinery. Every single drone packs roughly 200 grams of raw copper, 50 grams of optical gray glass, and dozens of trace precious metals, including solid gold for non-corrosive circuit contact points. The environmental cost and supply chain complexity of gathering these raw materials is staggering. Extracting just 1 single kilogram of neodymium produces over a ton of toxic residue and consumes over 2,000 liters of water. The global supply chain for these elements stretches across 18 countries, crossing 40,000 miles of ocean routes before a single screw is ever tightened. But what happens when these raw, chaotic elements finally collide inside the high-pressure vacuum of the factory furnace will leave you completely speechless. Step 1 of physical creation begins in the heat of the carbon fiber weave shop, where black threads are woven into multi-axial fabric mats. These carbon sheets are laid into precision-machined steel molds, flooded with liquid epoxy resin and slammed shut under a crushing hydraulic pressure of 15 bar, or over 215 psi. The molds are heated to exactly 180 degrees Celsius, 356 degrees Fahrenheit, for 45 minutes. You can hear the hiss of steam escaping and smell the sharp, pungent bite of curing chemical resins as the soft fabric bakes into a rigid, rock-hard chassis. Next, we step into motor winding chamber, where silence is shattered by the high-pitched whine of automated winding needles flying at 12,000 RPM. Thin copper wire is wrapped around laminated steel stator cores at a rate of 50 wraps per second, creating the electromagnetic coils that drive the propellers. Human operators clad in anti-static suits feed high-coercivity neodymium magnets into CNC mounting jigs, securing them with aerospace-grade acrylic adhesive cured under intense ultraviolet light for precisely 12 seconds. Smell the sweet, ozone scent of high-voltage static charge hanging heavy in the air as these motors are spun up to 30,000 RPM for their very first spin test. While the motors are spinning up, the drone's digital brain, the printed circuit board assembly, is being born inside a clean room running under positive air pressure. Pick-and-place robotics move like lightning, mounting over 3,000 microscopic surface mount components per minute onto bare green circuit boards. The board then enters a 10-zone reflow oven, baking at a peak temperature of 245 degrees Celsius for 90 seconds to melt the lead-free solder paste into permanent electrical bonds. What happens next surprised even experienced engineers. If a single solder ball shifts by more than 5 micrometers, the entire circuit board is automatically fried and ejected by a high-pressure air blast. Now comes a marriage of physical frame, electronics, and propulsion on the final assembly line. Factory technicians using torque-controlled pneumatic drivers set dozens of tiny titanium screws to an exact tolerance of 0.5 Newton meters. The multi-axis camera gimbal is mounted using soft silicone dampening balls to isolate the optical sensors from high-frequency motor vibrations. The entire assembly sequence takes exactly 24 minutes per drone, with over 60 individual units rolling off the single production line every hour, moving directly toward the ultimate test of survival. No human eye could possibly spot the microscopic flaws that could cause a drone to fall out of the sky, so ultra-advanced automation takes full control. Multi-axis 3D laser scanners sweep across every finished carbon fiber arm, mapping over 10 million spatial points in 5 seconds to verified tolerances within 2 microns. Next, AI vision cameras equipped with 50-megapixel sensors analyze every solder joint on the flight controller, comparing real-time imagery against a neural network trained on millions of circuit patterns. The rejection rate at this stage is kept strictly below 0.5%, ensuring absolute perfection before power is ever applied. Once passed by AI inspection, the drone enters the environmental torture chamber to simulate the worst conditions on Earth. Inside a sealed environmental cell, temperatures plunge to minus 20 degrees Celsius within 3 minutes, freezing water droplets onto the motor housings, before spiking up to 60 degrees Celsius with 95% humidity. The drone's internal IMU heat plates glow under infrared camera inspection as the flight control software recalibrates its internal gyroscopes under intense thermal stress. Listen closely, and you can hear the deep roar of giant environmental simulation fans blasting 40-knot turbulent winds directly into the drone's face. Despite the millions of dollars spent on AI inspection and automated climate chambers, there is one moment where human skill beats machines every single time. Meet the master gimbal calibration specialist, a human technician who tunes the delicate optical camera stabilization by hand. Using microdial indicators and personal tactile feel honed over decades, these specialists adjust the micro-tension springs that no digital algorithm can properly feel. If the physical feel is off by even a fraction of a gram millimeter, the camera footage will stutter during high-speed flight, making this human touch the ultimate gatekeeper of quality. Finally, every single drone must earn its international flight certification before being packed into its retail box. The drone is mounted onto a 3-axis dynamic shake table that vibrates at frequencies up to 2,000 Hz, simulating 10 years of severe flight turbulence in 30 seconds. Electric sensors record structural resonance, while laser tachometers measure motor output to ensure compliance with FAA, C, and ISO 9001 standards. But here's what nobody tells you. Even after passing every single one of these brutal stress tests, the most dangerous challenge of all awaits the drone outside the factory walls. To truly understand the drone explosion, you have to look at the staggering global numbers shaping our skies. Today, the global drone manufacturing market is valued at over $32 billion, with over 5 million civilian and commercial units produced every single year. China leads global manufacturing, producing roughly 70% of all commercial drones, followed by the United States at 12%, France at 5%, Germany at 4%, and Israel at 3%. Globally, over 350,000 engineers, software developers, and assembly line workers earn their living inside the sprawling high-tech industry. Think about how fast this world has moved over the last 50 years. In 1974, unmanned aerial vehicles were crude, heavy target drones built out of aluminum and powered by noisy two-stroke lawnmower engines. Today, a modern consumer drone packs more computing horsepower than the Apollo 11 moon landing spacecraft, running billions of operations per second on a lithium polymer battery smaller than a deck of cards. Over the next 10 years, global drone production is projected to skyrocket past $70 billion as fully autonomous delivery fleets take over urban skies. Here are 3 shocking facts that most people have never heard. First, the lithium polymer battery inside a high-performance drone discharges its stored electrical energy faster than a commercial electric car battery during full-throttle takeoff. Second, the tiny optical sensors on the bottom of a drone take 2,000 photos of the ground every second just to stay completely frozen in midair without GPS signal. And third, the carbon fiber used in a premium drone arm has a tensile strength 5 times stronger than structural steel, yet weighs less than a plastic bottle. From deep, dark, rare earth mines thousands of feet underground, through high-temperature curing ovens and lightning-fast robotic assembly, to the final razor-thin tolerances of laser calibration, we have traced the incredible birth of a flying machine. What begins as toxic mud, crude oil, and raw sand ultimately transforms into a marvel of modern flight that defies gravity at the press of a button. It is a seamless fusion of human ingenuity, global trade, and relentless technological perfection. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.